Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the online lecture on linear control systems. Today we are going to continue our discussion on time domain controller design. And so far we have discussed that we call it time domain design really because the desirable specifications are given in time domain. For example, the objectives of the control are in terms of the desirable rise time, settling time, percentage overshoot, which are the time domain requirement. But really the control system design itself is not in time domain, it is in the frequency domain, where we are using root locus. Root locus technique is a frequency domain technique. But we call it the design in time domain because the desirable specifications are in time domain. So controller design methods are not unique. I cannot stress enough on this point, but at least you learn one or two ways of designing the controller in these lectures, and then you can try your own new methods or learn new methods from other reference material, reference books. If P controller is so far we have learned that if P controller is unable to address the steady state error requirements, then the next choice of controller that you can try for the system is PI controller, because the integral part really helps in terms of steady state error, removal of the steady state error. Be careful about the order of the final system, because in professional projects fine-tuning of the gains is often required after the initial design. So we looked at this point at the end of the previous lecture, and we shall also be looking at this point in future as well. So this is what it is so far. So now we start with the design of PD controller. So far we have looked at the design of P controller and PI controller, and now today we look at the PD controller design. So design procedure: using root locus, choose the P part so that the steady state specifications are met, and then select the D part such that the transient requirements are satisfied. So in this PD type controller, the steady state error requirements are mostly satisfied using the P part of the controller, and some of the dynamic specifications are also satisfied using the P part, and remaining dynamic specifications can be satisfied using the D part. So how do we do that? Let's look at an example. Given the transfer function 1 over s square minus 1, so here the s term is missing in the transfer function, so you know straight away that there is no use of trying the P controller. We have to straight away go to the PD controller. So design the controller such that the steady state error with respect to step is less than 0.05, and this design specification is given in terms of the zeta, which is damping ratio, but this translates to the requirement that percentage overshoot should be less than equal to 5%. So sometimes requirement could be given in terms of zeta or omega n, but mostly the requirements shall be given in terms of the rise time, settling time, percentage overshoot, etc., from which you have to calculate the feasible ranges of zeta and omega n. So here we have this system. We need to design the controller. We don't know which controller would work and what gain values would be optimum or suitable, and we want steady state error with respect to step to be less than 0.05 and zeta to be greater than or equal to 0.707. So the solution is we try the PD controller straight away, as I said earlier, because there is an S term missing here, so there is no use of trying the proportional controller. So we know that the steady state error with respect to step is given by this expression. This we have learned in the previous lecture on steady state error for systems of different types, and when we plug in the limit, then we see that the steady state this limiting term becomes minus kp if you plug in all the values of C of s equal kp plus kds and g of s equal 1 over s square minus 1, and when you substitute s equal 0, then you get minus kp, and then the steady state error becomes 1 over 1 minus kp. And for that you can see that this steady state error would be less than or equal to 0.05 if kp is greater than 21. So here an important point is that for the steady state error, it does not matter, the sign of the error does not matter whether it is positive or negative. The real thing that matters is the magnitude of the error. So because we are studying the root locus for only positive gains, so that is why we are taking the positive value of this gain kp, which is kp for kp greater than equal to 21, the error would be, the magnitude of the error would be less than or equal to 0.05. If you keep on increasing kp further from 21 and onwards, the error value would further go closer and closer to the 0 value. So note that the sign does not matter for each steady state, it is the magnitude of the error that matters. And so we have g of s and c of s, and so far we have found out that in order to meet the steady state requirement, the p part of the controller shall be such that so that kp is greater than or equal to 21. Now we need to design the d part of the controller to meet the transient specifications. Okay, so for just the p part, if we use just the p part of the controller, then the closed loop characteristic equation for the system c of s into g of s divided by 1 plus c of s into g of s, where c of s is just kp, then the denominator of that closed loop transfer function would be s square plus kp minus 1. And this I am not going to derive here in these slides, because at this point I expect you to be able to calculate the closed loop characteristic equation on your own. So you just have to calculate this characteristic equation, and it will turn out to be the same thing that I have written on the slides. So s square plus 20, that is the closed loop characteristic equation with c of s equal just kp, and then this has the roots of plus minus j into square root of 20, which means both of the poles are on j omega axis. So remember that we have just designed the p part of the controller, we still have to design the d part. And so now the PD controller, with PD controller having the proportional part equal 21, the closed loop characteristic equation becomes something like this: s square plus kds plus 20 equals 0. And for this closed loop characteristic equation, we can actually use the root contour approach. Root contour approach says that if you have a characteristic equation of a system and there is an unknown parameter, you can basically design the root locus and see what happens to the roots of this equation with respect to this parameter. And this is exactly what we want to see. We want to see the closed loop, the roots of the closed loop characteristic equation with PD controller having p part equal 21 with respect to the change in the gain kd. So this analogy, I give you some time to digest this analogy, that we have basically we have designed the p part, and now with p part fixed and d part variable, we have written down the closed loop characteristic equation, and now we are treating the gain kd as the parameter that with respect to which we want to study the closed loop poles of the system. So in order to design the d part, we take the open loop transfer function with kp equal 21 and study the root locus for kds, for which, you know, here you separate out the kd terms and the non-kd terms. You will see that the non-kd terms are s square plus 20. S square plus 20 becomes your poles, and the kd terms, kd into s, becomes your zeros, and that is what we do in the root contour approach. So in root contour approach, we define a new transfer function, new open loop transfer function, that is basically derived from the closed loop characteristic equation. So there we have closed loop characteristic equation. We have used this equation to derive the new transfer function which corresponds to root contour. And root contour, this will tell us how the poles of this characteristic equation vary with respect to KD. Okay, so we have the transfer function, the control law, and the requirements, and now we have determined the new transfer function KD into S over S square plus 20, and now we sketch the root locus with respect to KD, and you can see that the poles start from plus square root of 20j and minus square root of 20j, which are the roots of this equation, and then we draw the root locus with respect to this gain KD. Both of the poles start moving towards the real axis, and they break in at maybe minus 4.5 or close to minus 4.5, and then one of the poles start moving towards the zero at the origin, which is represented by this S, and the other poles start moving towards the infinity at an asymptote of minus 180 degrees. Okay, so this is the root locus, and based on this root locus, you can see that here I have a data tip here which says that at gain 6.3 my poles are at minus 3.15 plus 3.18, where damping ratio is almost the same as what I need. I need zeta to be 0.707, which is fairly close to 0.704, and I also needed the steady state error less than 0.05. That has been taken care of with the help of KP, and now I have also taken care of the zeta. So it seems that the desirable value of zeta is achieved for KD greater than or equal to 6.3, and you can say select, to be on the safe side, you can select KD to be 6.4, and your final controller becomes 21 plus 6.4s, which is KP is 21 and KD is 6.4, that we have designed using the root contour approach. Okay, so the resulting closed loop transfer function becomes 21 plus 6.4s over s square plus 6.4s plus 20, and we are all set. We have met all the requirements, but let's just pause here and think about it a little bit in more detail. So this closed loop transfer function is, although it is second order, but this is not exactly similar to a standard second order transfer function. So there is a difference between this transfer function and a standard second order transfer function, but we have used the term zeta here, which applies to standard second order transfer functions. So there will be some inaccuracies, we can expect inaccuracies in the closed loop system but how can we get rid of these inaccuracies, and how can we move closer to our desirable standard form? So the standard form is omega n square over s square plus 2 zeta omega n s plus omega n square. Alright, so there is a difference that there is no zero here and there is a zero in the original closed loop system. So to achieve the standard form, we can use the pre-compensator. So this is a feed forward control law, and we have also already discussed pre-compensator in terms of pole zero cancellations and approximating higher order systems as the second order system. In this case, to match this standard form with this system, all we need to have is plus 20 on the numerator and get rid of this 21 plus 6.4s. So we do that with the pre-compensator, which is the 20 divided by 21 plus 6.4s. So this 21 plus 6.4s will cancel out with this one, and the plus 20 will come out here. So this is the series combination of feedback control system. So this basically is the closed loop system where I have packed the whole closed loop system into a single closed loop transfer function, and then this is the pre-compensator transfer function. If you use this pre-compensator controller, then this controller design that will remain the same, but overall system will behave like a system which is 20 divided by s square plus 6.4s plus 20, which is a standard second order system which is of this type, this form. So you can use pre-compensator to achieve the standard systems. This would be a 2 degree of freedom control, where you have a feedback control, feedback PD control 21 plus 6.4s, and you have another feed forward control 20 divided by 21 plus 6.4s. Okay, so this is one technique, and next we move on to PID control design. So the design procedure for PID control is to split the design of PID control into two controllers, one PD control and one PI control. So how do we do that? We shall see in a minute. So we design the PI control for steady state specifications and some of the dynamic specifications, and then we use PD controller to meet the remaining dynamic specifications. So here we have PID control Kp plus KdS plus Ki over S. If you simplify that, that becomes KdS square plus KpS plus Ki over S, and then we can split this controller into two different controllers. So this is exactly equal to 1 plus KD1S, which is a PD controller, times Kp2 plus Ki2 over S, which is a PI controller. So we can write a PID controller as a product of PD controller and a PI controller, where your Kp this Kp will be equal to Kp2 plus Kd1 times Ki2, and this Kd will be equal to Kd1 times Kp2, and Ki will be equal to Ki2. So if you substitute these equations into this left hand side, then left hand side on simplifications and multiplications, this will become exactly equal to the right hand side. So this is one way of designing PID controller that is very useful, that you decompose the PID control into a PD and a PI control. Okay, so we shall see through example how do we actually do this. So let's look at an example. Given the transfer function of the plant 1 over S into 0.1S plus 1 into 0.2S plus 1. So we have a third order system here, and we need to design the controller CS such that first of all, the error coefficient for the steady state error with respect to parabolic input is greater than or equal to 100. We discussed briefly about the error coefficients related to errors with respect to step input, parabolic input, and ramp input. Actually, this is the steady state error coefficient with respect to ramp input. So we discussed those in the lecture regarding steady state errors of for the systems of different types. So you can refer to that, or you can refer to your textbook. It has a very nice table drawn which indicates the steady state errors of for systems of different types and the steady state error coefficient values. So Kv is the error coefficient for the steady state error with respect to ramp. And then we have another requirement for this system, that overshoot for the closed loop system should be less than or equal to 5%, and the rise time should be less than or equal to 0.25 second, and the settling time should be less than or equal to 0.5 seconds. So these are the requirements for our system, this system, and we need to design the controller for that system. So first of all, we just do some simplifications. We take this 0.1 out as a common and this 0.2 out as a common. If you take 0.1 common from here, this will be 1 over 0.1, which is 10, and if you take 0.2 common from here, this will be 1 over 0.2, which is 5. So this will be s plus 5, s plus 10, and this 0.02 is basically 1 over 50. So this system will become 50 over s into s plus 10 into s plus 5. We will see that later on in this lecture. So try okay, there is no reason for us here to try a PD controller or a PI controller straight away, because there is no s term missing. Actually the constant term is missing, so which can be catered for using only the P controller. So wherever we can apply P controller, or wherever we don't have the clear reason to choose any higher order controller, we always start by designing the P controller only. Okay, so if you try the P controller, then the transfer function shall become Kp over 0.02s into s plus 10 into s plus 5, which you can write as 50 into Kp over s into s plus 10 into s plus 5. This is a third order system. And now you can see let the root locus gain k be equal to 50 times Kp, as we always do for simplicity, and then later on when we find the value of k using root locus, we will go back and find Kp using this expression. So for steady state requirements, Kv, which is the steady state error coefficient for ramp input, it is given by limit s approaches 0 s into GSHS. So here GSHS is k over s into s plus 10 into s plus 5. S into GSHS will be, if you put in s here, this will cancel out with the s in the denominator, and if you plug in the value of s equal 0 in the remaining transfer function, you will get k over 50. So k over 50 is the value of Kv, and we already know that we want Kv to be greater than 100. So we need Kv to be greater than 100. So for that we shall be needing k to be greater than 5000. So it means that we need the root locus gain to be greater than 5000 in order to achieve the steady state. Okay, so next we look at the root locus, and we see what happens when the gain is greater than 5000. Here is the root locus. So we have a pole at 0, one other pole at -5, and the third pole at -10. So this is a pole at 0, pole at -5, and pole at -10. You can see that there are no zeros in the system, so there will be 3 asymptotes. One will be at 180 degrees, other will be 60 degrees, and the other will be -60 degrees. So you can see that these poles move towards each other, they break away, and they move towards in the asymptotic fashion. And you can see that for gain, this is the gain value of 1.55 into 10 raised to the power 3, which is around about 1550. So with the gain value 1550, you can see already the pole has crossed the j omega axis, and the pole has moved on to the right half plane, which means that the closed loop system is no longer asymptotically stable. The closed loop system will be unstable. So this means that for k greater than 1500 or 1550, the peak we lose the stability, and we need k to be greater than 5000 in order to achieve the steady state specifications. So this means that P controller will not work in this case. So we have to next, because P controller is unable to achieve the steady state requirement, so next we have to try the PI controller. So but here I just would like to take a break, and we will continue this example in the next lecture, and we will see how we complete the controller design to meet all the specifications. At the end, I would just like to revise the whole lecture so that you know what we have discussed so far. So this is the second lecture in the series of lectures on time domain controller design, and today we started our discussion with the previous findings that so far we know that the time domain controller design means that the desirable specifications are in time domain. controller design methods are not unique, and the P controller, if it does not work in terms of steady state error, then we have to try PI controller, that we learned in the previous lecture, where we looked at the design of P controller and PI controller. And we also looked at the previous lecture that we have to be careful about the final system order and final system the shape of the transfer function, the closed loop transfer function after the design of the controller. In this lecture we have looked at one solution to make the final closed loop system to be similar to the standard second order system. The design procedure, we looked at the design procedure for PD controller, where we saw that we designed the P part to meet the steady state requirements, and then we designed the D part to meet the transient requirements. And then we looked at an example of second order, where we have s square equal plus 1. So there are two roots in the system at plus minus 1. So the one of the poles is at plus 1 and one of the poles is at minus 1, and we need this system to be asymptotically stable with steady state error less than 0.05 and zeta to be greater than 0.07. We looked at the formula for steady state error. We plugged in the formula. We looked at the values of Kp that will render the absolute value of the error to be less than the desirable range. And then you see that we found the value of Kp that is suitable for the steady state error requirements. And then once we found the value of Kp, then we looked at where the closed loop poles are with just the Kp part. The poles are at plus minus j into square root of 20. And then we looked at where the closed loop pole could be with the Kp fixed at 21 and Kd as our design parameter. So if Kd is a design parameter, we use the theory that we learned about the root contour, and we use the root contour approach, and then we formed a new open loop transfer function from the closed loop characteristic equation. Okay, so this new open loop transfer function gave us the root locus for different values of Kd, which is basically the closed loop poles of the original transfer function, and the controller with different values of Kd. And then we have designed the controller that meets all the specifications. But then we compared this final closed loop transfer function with the standard form, and we saw that there are differences, and we also discussed how to get rid of those differences with the help of precompensators that cancels out undesirable poles and zeros. And here the caution is that you can only cancel the poles and zeros that are in open left half plane, but rather to be careful, you do not even cancel any pole or zero which is in the left half plane but too close to j omega axis. So in this case, this zero is fairly far away from the j omega axis, which is like this zero is at minus 21 over 6.4, which is more than which is less than minus 3. So it is quite far away from the j omega axis and into the open left half plane, so it is okay to cancel out this zero. And then we looked at the PID design, and we discussed that the PID design is always done by decomposing the PID controller into PI and PD controllers, and we split the PID controller into product of PD controller and PI controller with these translation equations. So these are the equations that give you translation of PID gains onto the this PD controller and PI controller gains. Okay, then we started to look at an example of a third order system where we have some desirable specifications, and we try to meet those specifications with different controllers that we try to implement on this system. And then we looked at P controller first, as we always do, and then we first of all looked at the steady state requirements, and the steady state requirements could be met using the gain to be greater than 5000, And when we looked at the root locus showed that for the gain greater than 1500, the poles already cross the j omega axis and move on to the right half plane, so there is no possibility of it using the gain 5000 or greater than 5000. And this shows us that P controller would not work, and we will continue this discussion and this example in the next lecture. Thank you for listening. Let me know if you have any questions related to this lecture.